Oh, classes. Okay, so last time we talked about bending of light when it passes from one medium to another. So particularly we look at going from air to glass. And air has an index of refraction that is effectively just equal to 1, but glass is 1.5. So light bends towards the normal when it moves from air to glass. Actually, before talking about curved lenses, let's look at an example. Say we have a flat sheet of glass, something like a window. Now, if light comes in, I'm going to extend the window a little bit. So windows are usually thin compared to the other dimensions, just for purposes of the drawing. Say light comes in at an angle, and what's going to happen is it's going to bend towards the normal. So the question is, does light get distorted by the window? And the answer is not really. Let's just say this is NG for glass. Outside, the index of refraction is just 1. And so what happens when light hits a window at a certain angle, it's going to bend towards the normal, but then when it hits the other surface, it's going to go from a high index of refraction to a low index of refraction and bend away from the normal. And it's easy to see that these two beams are going to be parallel. So to do that, let's say this is theta 1, and this angle is theta 2. So applying Snell's law, we have n1, which is just 1. So we have sine of theta 1. That would equal ng times sine theta 2. Now again, this is a window. These two sides are parallel to each other, and that makes these two angles equal to each other, these two. So this angle is also theta 2. So now if we look at, this is our angle of incidence. Here we have ng sine of theta 2. Let's call this angle theta 3. So again, that would be n for error, which is 1, so that would just be sine theta 3. Now, these are equal to each other. So what we have is sine of theta 1 equals sine of theta 3, or theta 1 equals theta 3. Just purely mathematically, this does not follow from this, but these are obviously angles between 0 and 90 degrees, and so, the only way that's possible, if the sines are equal, the angles must be equal as well. Okay, so flat surfaces do not bend the light overall. Whatever angle it's coming in, it's going to leave. You could say there's a little bit of an offset, but for a thin window, no, nothing really happens. You can just consider it passing through the window without any real distortion. Now, what if we have a curved glass surface, and we can use that to focus light? So we're going to look at two main types of lenses. I think I'll draw it off to the side. We have a converging lens that looks like this, where we can draw an axis through the center, and any beam of light parallel to that axis is going to convert, they're all going to converge at this point called the focal point. Again, these lenses are designed to converge all the light, so there's a precise, mathematical shape here that'll converge all the light to that one point. And we can also have a diverging lens, and has this hourglass look. And the light coming parallel to this axis is going to diverge. And if you trace these rays back, they're all going to come as if they were emerging from one point. That'll be the focal point for a diverging lens. So for a converging lens, it actually focuses on the light at that point. For a diverging lens, it appears that the light is coming from that point. And we're only going to consider thin lenses. There are other types of lenses. You could have something that looks like this, where it's got some thickness to it, and then these curved surfaces. You could have one that's kind of like that, except an hourglass shape. There's all different types. One, not really curved, but something else that's very common is a prism. And we talked about an object like this, where it does not change the angle of the ray. That's because these two sides are parallel. In a prism, these are not parallel, so you get this net bending of light when it passes through a prism. Now, something I didn't mention earlier, the index of refraction, if you look it up, for glass or something, it just says the index of refraction is 1.5 whatever. You have to always read the fine print when you look up tables. Those were taken for a particular wavelength of light, so that value. So the index of refraction actually has different values for different wavelengths of light, and that's why prisms work the way they do. If you shine light on a prism, it separates them into colors, and that's because different colors of light are bent through different angles. So, let's get to our converging and diverging lenses. Kind of similar to what we did with mirrors. We're going to focus this video on just these ray diagrams. We'll start with a converging lens. So it's very similar to what we did with mirrors, except now light can pass either direction. So we have a focal point on each side. So we draw our lens like this. We have a focal point on each side. And let's say we have our object here, and we want to know what the image looks like. So there's, just like before, we have three special rays that we can draw. So the first one, parallel to the principal axis, and then through the focal point on the opposite side. So that would be ray 1. Now the second one goes through the focal point on the left side, and then it comes out parallel to the principal axis. So that would be 2. And ray 3 goes right through the center. And surprisingly, this was actually an adequate drawing. Works a little better with lenses than with mirrors, because these lenses are thin. And so you can just treat it like a line and only draw the lens itself, so we can see it's a converging lens and not a diverging lens. When it comes to ray diagrams for curved surface, for mirrors, you need to get the curvature right, or the ray diagram won't work too well either. But anyways, this would be our image where these three converge. So here we have a real inverted image. As far as the magnification, I'm not going to say, because it's hard to tell. Looks about the same size. Could be a little bigger, smaller, depending on where we put this object. So, and again, that simulation I posted, I'll double check. I'm pretty sure we can use it for lenses as well. So you can just click, switch from a mirror to a lens and play around with that as well. But I also want to look at what happens if we move the object so it's on the other side of the focal length. So let's do that. And then we'll look at diverging lenses as well. So I'll draw basically the same picture. focal points on each side. So we start out normally, parallel to the principal axis, through the focal point on the right. Now, the other one's going to be a little more difficult. Well, for two reasons. One's not really a big deal, but yeah, the other one, when we were over here, we went through the focal point on the left. So here, we're going to do that, but going the opposite direction. So we go away from the focal point, and when we hit the mirror, then we have it go parallel to the principal axis. Now, we didn't actually hit the mirror, but I could have just drawn it a little bigger. Doesn't matter if we actually hit it or not. You know, it's just this. The mirror's at a particular location, or the lens, sorry. Now, maybe if you have a small lens, you know, that could cause some problems, like you have to put your eye in just the right spot to see things. But, yeah, it doesn't matter. Yeah. So, ray 1, always parallel to the principal axis, through the focal point on the other side. Ray 2, you either go to the focal point or come from the focal point, depending on what you need to do, towards the lens, and then parallel to the principal axis. And we can see these two are definitely not going to converge. So we have to trace them backwards. And we should get a virtual image here. And then just like before, ray 3. I should label these 1, 2, and 3. So again, if we trace this backwards, fairly reasonable. They all met up roughly in the same place. So this would be the image, which is magnified. Basically what we're describing here is a magnifying glass. So, oh wait, now let's think if we actually did that. We have the object before the focal point. I guess, no, it didn't quite describe a magnifying glass here because, you know, if you put like a book here, it'd be like holding it behind. Sorry, but this type of thing is a magnifying glass, just not this particular setup. But yeah, we did create a virtual image here. Okay, so converging lenses, we considered an object on each side of the focal point because the rays just look a little bit different. So now let's look at a diverging lens for both of these cases as well. So here's our lens. So we put a focal point on each side. Start with our object over here. And as always, ray 1. We start out parallel to the principal axis. And it's a, you know, you can see from the picture, we're going to go away from the focal point on the left. Now, for ray 2, what we're going to do is we're going to go towards the focal point. So we're going to go in that direction. So if the lens wasn't there, we'd go through this focal point. Except now it's going to come through parallel to the principal axis. So that is ray 2. And again, these two are clearly diverging. So we'd have to trace this one backwards. And it looks like our image is going to be here. And as one final check, let's go right through the center. And yeah, works out these three kind of meet up at this point. And so this is what our image would look like. So again, we have an object far away. So yeah, the image would be virtual and upright. Now, and as a final thing, let's consider, yeah, I guess in this case, we're looking at it from over here. So yeah, you'd see a little upright image. Yeah, now I'm thinking back, I think that last one would be a magnifying glass if we had a converging lens. But yeah, let's consider this diagram now if we put this, put the object in between the focal point and the lens itself. So let's consider that case. So we've got a focal point on each side. Let's put our object here. So to start out, always parallel to the principal axis, and then we diverge from this focal point on the left. So yeah, this one really isn't going to be any different than the other one, but yeah, and then we go towards the we go in this direction towards the focal point on the other side. Yeah, so nothing really different about this case. And it almost looks like the image and the object overlap here. And the third goes through the center. So yeah, just the way I picked for the location, they kind of overlap, so it's hard to see. I wonder if I can move it. Keep as much of this as possible. Yeah, let's try this. See if we get something a little more where the object and the image are easier to distinguish. Okay, so we use the focal point on the left to get ray 1. For ray 2, we do this. We go towards the other focal point and then trace backwards. So yeah, this one, this is our object. And then the third one goes through the center. So they all converge right around here. That would be our image. Okay. So again, a virtual image because we had to trace backwards to get where the light converged. So yeah, this would be a virtual image. All right, so yeah, this topic is just about the ray diagrams, and next we're going to use these ray diagrams to derive an equation. So again, just very similar to what we did with mirrors, but now we're doing that with lenses. But that'll be the next video.